Welcome to challenge number 7, and I would like to use this kind of pseudo design. It is not a design of a robot, but it basically is a couple of wheels and a ball. So I have a wheel here, I have a wheel here, and I have a ball. All of these are resting on this plane, which would be the ground. So if I were to peek up and look at it from a side view, we would see that the ball and the wheels are at about the same height. So the wheels are about the diameter of the ball. If I look at it from a top view, I'll go up in here, and then we would see that the wheels and the ball are in this relationship. Let's zoom in a little bit. We see these little arrows, the arrow on the left wheel and an arrow on the right wheel, and these arrows show the direction of spin. So the left-hand wheel is spinning clockwise, and the right-hand wheel is spinning counterclockwise. And that's pretty important. Actually, it makes the design a little bit harder, but that's okay. So we're going to run over here and we're going to look at the ball. Oh, before we look at the ball, the robot's back in here somewhere. Okay, but since this is just talking about the physics of the two-wheel pickup, I'm not concerned about the robot or how these wheels, what the motor that's causing these wheels to turn, or any of the other things. I'm just looking at the physics now. Then I have to build those other things in part of my design. Or actually, you have to do that. So let's go over to the ball. The ball is moving around, okay, here, and the robot generally moves into the ball. But I'm not going to move. I'm going to move the ball and to the robot because it's easier to move the ball. So I have the ball here, and let's just look at the ball's interaction. Excuse me, ball's interaction with just one of these wheels. So I go down here. If the ball hits the wheel like this, if the wheel is not spinning, the ball will simply bounce off the wheel. If the wheel is spinning, what happens is the wheel will apply a tangential force to the ball, and the tangent is right here, in the direction of the spin. So the ball will have a tendency to go off into this direction. If we were to hit the ball, if the ball were to come over like this, we would end up moving a little bit over in this direction. So the ball, when the ball interacts with the wheel, the friction of the spinning wheel against the ball will cause the ball to move. Now let's put the ball over here. Let's say the ball's here and it bounces off of the wheel, let's say here. So it would cause the ball to move in this direction. Now if the ball is moving this direction, it'll stay in contact with the wheel, but more importantly, it's going to hit this wheel. And so what happens now, both of the wheels will be putting a force on the ball. In both cases, the force is downward. Okay, so the wheels are trying to push the ball towards the robot. Now, something that's really important here is these are not just any old wheel. These are compliant wheels. And compliant wheels say they're squishy. So they will change the shape to comply with the ball, the interaction of the ball. So what happens, and also, by the way, most balls are squishy on this thing, unless it's like a billiard ball or a pool ball. And so what happens as these two wheels are turning, they will push the ball in this direction. Now, you say, but hold it, look at it. The ball has a diameter that's wider than the spacing on the wheels. And that's true, but the wheels are complying. The wheels are changing shape a little bit. And so this continues until this happens. At the time this happens, neither wheel is touching the ball. And so the ball, if it's been moving, it stays moving. And so it'll stay moving towards the robot. If I were to put some kind of a backing here, and let's do it up like this. If I were to put a wall here, the ball will hit that wall, and what will it do? It'll just stay there. okay, as the wheels spin against the ball. Now, making the wheels spin against the ball is not particularly a good idea, and so generally we would use some kind of mechanism or some kind of sensor, say the ball is in between those wheels, and we'd stop the wheels. And if that's the case, the ball will just be trapped by these two wheels. So this is the basis of a two-wheel intake. And it not only will do balls, it'll do all kinds of things. So we can attack all we can pick up irregular shapes. It has a hard time if it's too irregular, but for anything that's certainly with circular cross section, so, for example, here, see the circular cross section of this sphere? For example, a cone. It'll pick up cones just fine. It'll pick up cylinders. It'll pick up these kinds of things. It'll even pick up cubes, okay, if the geometries are right. So this is a nice way of doing it. Now, why do I like this particular thing? Because let's look at the ball. If the ball is doing this, it will be captured. If the ball is doing this, it will be captured. So you do not have to accurately place the robot into this. You do not have to center the ball into the robot before it strikes those wheels. The wheels have a tendency to be self-centering, which is really a cool piece on this. And also, to be honest with you, spinning wheels are pretty easy things to do with robots. Now, what are the things we need to think about with this design? Well, let's flip it up here. And the main thing is you got to get the wheels nicely positioned with the ball. So if I'm looking at it this way, let me get it all squared. So I'm going to use this. Remember, I can use this to present my cube, and then I could do this to center it. Okay, so I get a nice side view here. So what's happening here is the height of the wheels want to be about the diameter of the ball. And so if the wheels are below the diameter of the ball, it has a tendency to push the ball up. If the wheels are above the diameter of the ball, when the ball interacts with the wheel, it has a tendency to squish the ball down. So you need this to be about centered. The other thing is you need to look at from this view, how the wheels are centered, the center to the center distance on the wheels, which is actually, it's a circumference to circumference distance on this wheel. They need to be, that distance needs to be small enough that both wheels will contact the ball. Obviously, if we were to move the wheel on the right over to the further to the right, then this ball will not simultaneously contact both wheels, and that would not give you a very good intake. It would behave pretty bizarrely. But if these wheels are too close together, then the problem is it'll take too much force to squish these wheels, or the wheels are not compliant enough to do this. And so we need to think about what is that kind of optimal distance between the wheels. Another consideration is how squishy the wheels are. And you say, how do we measure squishiness? Well, we have two different squishiness on the wheels, and the more squishy it is, the more it deforms, or the less force it takes to deform. And so you could experiment between a squishy and a really squishy wheels and see what those would do. And the trick here is that if the wheels are too squishy, they deform too much and you won't get much force on the ball. If they're not squishy enough, the ball has a tendency to get stuck between the wheels. And then the final piece is how fast are the wheels moving. And at first you think, well, that's not particularly important. You know, if we go up here, let me get my top view again. Go here, get a nice top view. I believe this is it. No, it was not. Okay, let me roll this around. Just do it the old-fashioned way. Okay, let me get a top view here. Okay, there we go. If these wheels are rolling very slowly, what happens when this ball hits this wheel, the ball does not move very fast. It does not get much force, or it does not develop much speed in the tangent to that collision in this direction. So the ball has a tendency just to bounce off of it. And so if the wheels are spinning fast enough, then the ball gets anywhere near this wheel, the wheel will flip the ball very quickly in between these two. And of course, the similar argument goes on this side, right? I'm just using either, it's symmetric as you think about it. So these wheels generally spin fast. Okay, and a matter of fact, many times they spin faster than the drive wheels. A drive wheel on a robot, or an FTC robot, may spin, let's say, let's see, what are they? They're a foot. It may spin 4 revolutions per second. These 4 or 5 revolutions per second. These wheels have a tendency to spin maybe an order of magnitude faster. So these wheels have a tendency to spin fairly quickly. And for that reason, we're using a motor that we can adjust the gear ratios on. So that means we can spin it faster or slower. Okay, but this is what you need to build. You need to build something that basically will pick up a ball. And what it does with the ball, or acquires the ball. What it does with the ball, it can either capture it or can flip it into the robot and have another mechanism take care of it from there. Okay, with that, I think you have enough to see how the physics of this works and some of the considerations. And then now you have to do actually the hard part, and that's to design a mechanism that would support these two wheels and support the rotation of those wheels. Okay, so with this, I think we're done.